Swayam Prabha. Digital India. Educated India.
In this lecture, I am going to discuss the work energy relation for planar kinetics. To give you an overview of what we are going to discuss, we are going to derive the work energy relations from equations of motion of plane kinetics, look at the conservation of energy, and then look at some problems. Just to recapitulate what we had discussed for a system of particles, because this is what we are going to extend to rigid bodies. Here we had written out the Newton's second law for all the particles. We had n particles, suppose we have n particles, we write down the Newton's second law for all these particles, and we had taken dot product of each of these equations with the corresponding velocity of that particle. So, first equation gets a dot product with r 1 dot, and so on. The nth particle equation is dot producted with the velocity of the nth particle. And then we had summed up and we found that the rate of change of kinetic energy is equal to the power, and for rigid bodies this was taken as a special case. For rigid bodies, this contribution of internal forces is 0, because the internal force direction and the relative velocity direction for rigid bodies they are orthogonal, because remember the relative velocity r I dot minus r j dot is omega cross r I minus r j. Therefore, r I dot, this relative velocity, is perpendicular to the line joining the 2 points, and f I j is along the line joining the 2 points. Therefore, it is a dot product of two perpendicular or orthogonal things, and that is 0. And then we had looked at the decomposition of the kinetic energy expression, and we have found that the total kinetic energy of this system is equal to the kinetic energy of translation of center of mass with all the mass concentrated at the center of mass, as if center of mass is a point particle, and we are writing the kinetic energy of the point particle. This is one term in that expression of total kinetic energy. The second term comes from motion of the particles about the center of mass, and for rigid bodies this rho I dot will be related in terms of the angular velocity. So, this was the expression of kinetic energy of translation of center of mass, and kinetic energy of motion about the center of mass. Kinetic energy because of motion of the particles about the center of mass. Remember that rho I dot is the relative velocity of the ith particle with respect to the center of mass. Therefore, the second term in the kinetic energy expression gives us the kinetic energy because of motion of the particles about the center of mass. For rigid bodies, this can be written very simply like this: omega cross rho I. This follows from our discussions on kinematics, because the center of mass and the point particle, ith point particle, both are parts of a rigid body. Therefore, the relative velocity is omega cross the relative vector, which is rho I. For rigid bodies, that summation goes over to an integral, and our measure for this integration is the small mass of that particle, infinitesimal particle that we are considering, dm. As you can see, the first integral is because of the motion of center of mass. It is the velocity of center of mass square 1/2 of dm times velocity of center of mass square integrated over the whole body. The second term is 1/2 omega cross rho dot omega cross rho dm. Now, this is because of the rotation of the body about the center of mass. This is sometimes called the rotational kinetic energy. and we will see this detailed expression. Now, here I can look at this term as a scalar triple product. I can look at this expression as a scalar triple product. What I do is I see that this is A cross B dot C. This is scalar triple product, and this can be written by rotational permutation. You can write it as, I can take this C in place of B, therefore, this becomes equal to B cross C dot A. So, this becomes B cross C dot A. Therefore, this term, this vector goes here, this vector goes here, and the vector A goes here. Right? This is cyclic permutation. That is what I use. Here C vector is this whole thing. Therefore, if I use that, I can write it as, so first term it's integration of dm. Integration of dm is nothing but the total mass of the system. The second integral can be written, because this omega goes here. So, this comes here, and this omega cross rho goes to the second place. So, this is omega cross rho, and rho goes to the first place. So, here sits rho. And that is integrated over the mass, total body. This expression you have seen before, and the first term is straightforward, it is the translational kinetic energy because of the translation of the center of mass. The second one, this bracketed quantity, the bracketed quantity happens to be Ig times omega. This we have discussed before. This happens to be Ig times omega, the moment of inertia about the center of mass of the rigid body times the omega vector. Now, since we are discussing planar kinetics, Ig is a scalar quantity, but planar kinetics for prismatic bodies. Therefore, the expression of total kinetic energy of this prismatic rigid body, you can think, is 1/2 m Vg square plus 1/2 omega dot Ig times omega. Here as an expression, Ig can also be a tensor, the moment of inertia tensor, which we will discuss a little later. But for prismatic bodies, this will turn out to be a scalar. Therefore, we have these two terms, the kinetic energy of translation and kinetic energy of rotation, that constitutes the net kinetic energy of the body. Now, the power expression we had written like this: force times velocity, force dot velocity vector, and when I write R I dot in terms of the velocity of center of mass and the relative velocity, for the rigid bodies, as you know, the relative velocity is omega cross the relative vector rho I, and if you substitute these things in the power expression as I have done here, the first term, when I open these brackets, the first term, it will be only summation of Fi, because Rg has nothing to do with the summation. Therefore, I will get the net force dot velocity of the center of mass plus there will be a summation here, which I am going to again do some processing. I am going to use, this is again a scalar triple product. The first term is simple, it is net force dot velocity of the center of mass, whereas the second summation I can use the scalar triple product, and I can rotate this in this form, write it like omega dot summation of rho I cross f. What is rho I cross f? Fi. Fi is the force on the ith particle. Recall that Fi is the force on the ith particle. Therefore, rho I cross f, this is nothing but the moment because of the force on the ith particle, moment about the center of mass. Therefore, the net power is equal to net force dot velocity of center of mass plus net moment about the center of mass dot omega, and this moment can include couple moments as well. So, that is the power expression, and our work energy relation turns out to be rate of change of kinetic energy is equal to the power. And if when I do these substitutions, I get this as my final expression. Therefore, if I integrate over time, on the left I will get the change in kinetic energy. Now, this kinetic energy, change in kinetic energy means total kinetic energy, rotation, translation and rotation. So, T indicates the total kinetic energy of translation and rotation, this total sum. The change in this sum is equal to F dot dr, which is work done on the system by the forces, net force, and this is of course, this is on the center of mass. And the second integral mg dot omega dt, I have not written here omega as some theta dot k cap. If I do, then I can write as mg d theta, but in general, for a general rigid body, I cannot write omega as a time derivative of a vector quantity. Omega is not time derivative of a vector quantity. A general omega is not time derivative of a vector quantity, but for planar rotation, when I write omega as theta dot k cap, for planar motion I write omega as theta dot k cap. In this case, I can do this integral. So, omega dt in this case, omega dt I can write as d theta k cap. Okay. This is only for planar rotation, not in general. I cannot do this. Now, the kinetic energy is of course composed of the translational part and the rotational part, and we are going to look at this distribution of or how the translational kinetic energy changes and how rotational kinetic energy changes a little later. If you consider planar rotation about a fixed axis, then there are some simplifications possible that I was mentioning. Now, velocity of center of mass can be written as omega cross r g, and you note what is r g here. This is r g vector from O to the center of mass. Velocity of center of mass is omega cross r g, and therefore, velocity of the center of mass square is omega square r g square, and omega has this form. And then I substitute this here, I substitute these expressions here, and I use once again that scalar triple product rotation, because of scalar triple product I can do this rotation, and on the left hand side I have d dt of the bracketed quantity. You will notice, what is the bracketed quantity? The bracketed quantity is 1/2 m r g square plus I g times omega g, oh sorry, omega square. This is nothing but the parallel axis theorem to shift or to find out the moment of inertia of the body about O. Therefore, this is I O. Therefore, half moment of inertia about O times omega square is the net kinetic energy of the body, and on the right hand side, by using this rotation, I can write it omega dot r g cross f plus m g dot omega, and this I can write as if I take this omega dot outside common, then I have r g cross f plus m g, which I have written out already, and this dot omega, and omega is omega k cap. You should note one thing in these in this expression and also here, the net force at the center of mass includes the hinge reaction forces. The net force at the center of mass includes the hinge reaction forces. Similarly, the moment at the center of mass because of all forces will include the moment because of the hinge reaction forces. Therefore, this I have mentioned contribution of the hinge reaction forces, but when I finally do this about the center of mass, I get m o net moment about the hinge times omega, and here those forces, the hinge reaction forces, will not contribute. Therefore, it is very easy for rotation with a fixed axis rotation problem. It is always good to apply at the hinge. Therefore, this is the total kinetic energy in fixed axis rotation. So, this is our expression. Now, here I can write omega as theta dot k cap, which I had written previously. The omega vector was theta dot k cap, because this is planar motion, and in that I can write it like this. Therefore, this dt omega vector dt, this is what I will have here, and that turns out to be theta dot dt k cap, and everything is in k cap direction. Actually, everything here is a scalar. Finally, it has reduced to a scalar because I have taken a dot product, because this moment is also in the k cap direction. Therefore, I had the dot product, and finally, everything reduced to a scalar quantity. Now, this is the net change in the kinetic energy, which can be written as the kinetic energy calculated about the hinged point. So, change in kinetic energy of the body is equal to the net moment about the hinge point. This is the work done because of the moment about the hinge point. The integral m o d theta, when theta goes from theta 1 to theta 2, is the net work done by the moment, and therefore, the change in kinetic energy of this body is equal to the work done by the all the moments acting. There can be couple moments, there can be forces whose moment you can calculate about O, and you have to calculate the work done by these moments, and that must be equal to the change in the kinetic energy of the body. Let us look at the equation of motion of this rigid body about with the rotational dynamics equation or the angular momentum equation about g. So, we have the translational dynamics equation, which is the extended Newton's second law for the center of mass, and the angular momentum equation about the center of mass. And you know that the linear momentum of the center of mass is defined this way: the total mass times velocity of center of mass. And the angular momentum, we have defined it this way about g, it is arm cross the relative velocity dm for a rigid body, and for a rigid body rho dot, the relative velocity is omega cross rho. And we had used this vector identity to finally obtain the angular momentum in a simple form as I g, the moment of inertia about g times omega. I g is the moment of inertia about g. And if you consider this expression of omega, representation of omega as some theta dot k cap, then I have the moment of inertia about the z axis, that is the precise definition, times theta dot k cap for the planar situation is equal to h g, the angular momentum about g. Okay. Now, we have the translational dynamics. If I take dot product of this translational dynamics with the velocity of center of mass, then what do you have? On my left hand side, I have mass times acceleration of center of mass dot velocity of center of mass is equal to, on the right hand side, force dot velocity of center of mass. The left hand side can be written as d dt of the translational kinetic energy. Now, you see that we are only, if I use only the translational equation of motion or the extended Newton's second law and do that same processing as we have done before, consider this as a particle and dot product with the velocity of that particle, then I obtain d dt of the translational kinetic energy, and that is equal to, on the right hand side, it is the power, the force, net force on the body dot the velocity of the center of mass. Therefore, I can integrate and I can write that the change in the translational kinetic energy is equal to the work done by all forces at the center of mass. The F dot d r g is the work done by all forces, and that I integrate as the system moves from state 1 to state 2. So, that changes the translational kinetic energy of the system. What changes the rotational kinetic energy? For that, we have to look at the angular momentum equation. In the planar case, we are treating the thing for the planar case. I take a dot product of the angular momentum equation with omega. For the planar case, the moment about the center of mass, moment of all forces about center of mass will be in the k cap direction. Therefore, its representation will be m g k cap. I have taken dot product with omega, and I have written actually omega as theta dot, omega vector as theta dot k cap, and the angular momentum is I g z z theta dot k cap, and its time derivative is therefore I g z z theta double dot. On the left hand side, therefore, I have this theta double dot k cap dot theta dot k cap, that gives me this product, and on the right hand side I have m g vector dot omega, which turns out to be this with these expressions. Therefore, the left hand side I can write d dt of half I g z z theta dot square which you will recognize is the rotational kinetic energy. The bracketed term is the rotational kinetic energy, and on the right hand side it is the power fed because of the moments about the center of mass, because of all the moments about the center of mass. Therefore, rate of change of the rotational kinetic energy is equal to moment times the angular velocity. Hence, the change in the rotational kinetic energy is equal to the work done by all forces and maybe couple moments in changing the orientation of the body. It goes from state 1 to state 2, and that changes the rotational kinetic energy. Let us look at this problem. This is taken from the book of Merriam and Craig Dynamics. A uniform rectangular plate of mass 300 kilogram is supported in the vertical plane by two parallel identical links of negligible mass and a cable AC as shown. The cable AC, which goes diagonally from A to C, is to prevent the mechanism from falling down. If the cable suddenly breaks, determine the angular velocity omega of the links an instant before the plate strikes the horizontal surface E, and DC is horizontal. So, the link DC becomes horizontal just before it strikes the ground. Also find the force in member DC at the same instant. This plate is of course a prismatic body, and we are considering the motion in the plane which contains the center of mass of the plate. The forces that are acting on the plate, external forces, are because of the links of course and the weight. Weight is a potential force because of the gravitational force, and we consider uniform gravitational field, and there is a potential corresponding to it. We look at conservation of mechanical energy of the system. The links are rigid and massless, therefore, they do not contribute to the mechanical energy, but the plate is massive, and therefore, we have to deal with the total mechanical energy of the plate, and that is conserved because we have this gravitational field which is a potential field. Therefore, the total mechanical energy at the initial state, when it is tied like this by the string, and after the string has broken and the plate is about to hit the ground, we consider the total mechanical energy at that state. So, just after the string is broken, it starts from rest at this configuration, and the second state is just before it hits the ground. The initial kinetic energy is of course 0 because it starts from rest at t equal to 0 plus, it is at rest at t equal to 0 the string breaks and the initial the velocity is 0 at that instant. The initial potential energy, which is V1, is measured from the datum. The datum I have shown here, the ground is the datum, and you can easily see that mgh, height of the center of mass from the datum, is L sin 30 degree plus h by 2. Therefore, this is the initial potential energy just after the string breaks, and that must be equal to the total mechanical energy when it just before it hits the ground. It has a velocity v, therefore, the kinetic energy of the plate is half mv square. Now, notice that this plate is in curvilinear translation, there is no rotation of the plate because the mechanism is such, it is a parallelogram mechanism. The mechanism is such that it will not allow rotation. This is a parallelogram mechanism, therefore, this edge and this edge, they will remain parallel, and that is why there is no rotation of the plate. Therefore, it is only the translational kinetic energy half m velocity of center of mass square plus the final potential energy, it is mg h by 2, that is the height from the datum of the center of mass. If you do the simplification and carry out this calculation, you will find velocity is under root g L, and that must also be equal to length of this member times omega. This is purely from kinematics. This member now has become horizontal. This is in the final state. This member has become horizontal, and the velocity that we have at this point, which we indicate by v, which is same as the velocity of the center of mass. Why? Because the body is not in rotation, there is only translation. In a translating body, every point moves with the same velocity. Therefore, this point C has the same velocity as g, which is v, and this v must be this length times omega. And if you calculate omega from here by plugging in the values that are provided, you will get omega as 3.5 radian per second. That is about determination of omega. Next, we move to determine the forces in the force in that member that connects at C, the member DC. For that, I am going to write the rotational dynamics of this plate in the second configuration or state 2, and I will use the point B. Why I use the point B? Because the angular momentum equation about B is the moment of inertia of the plate about B times angular acceleration plus Bg cross mass of the plate times acceleration of B, that is equal to the net moment about B. Since we want to find out force in member at point C in member DC, we want to find out force in member C. I am considering point B because about that point Fc and the weight, these are the only two forces that contribute to the moment about B. Weight is known, the only thing then the unknown would be Fc. Also note one more thing, since the links are massless, therefore, they form what are known as two force members. In mechanics, these are called two force members. If this is that link, then the force on that member CD is like this. This is a two force member. Therefore, the force on the plate at point C will be horizontal, because we are dealing with state 2 where the link DC has become horizontal. Okay. Now, angular acceleration of course is 0, angular velocity of the plate is also 0. Therefore, IB times alpha, that drops out. The rest of the terms I can write, I can represent Bg vector in the coordinate frame that I have chosen, because the dimensions of the body are specified, cross mass of the plate 300 kilogram times acceleration of point B. Note that B is moving on a circular path. B is moving on a circular path with A as the center. Therefore, this is moving on this circular path. Therefore, the acceleration of point B will have two components, one is tangential to the path, the other is normal to the path. normal to the path is in the negative x direction, therefore, and that is the centripetal acceleration minus L omega square I cap, that is the centripetal acceleration term, plus this is the tangential acceleration L omega dot j cap. This is angular velocity and angular acceleration of the link. If I write down the right hand side of this equation, angular momentum equation, is the moment of all forces about B. Two forces will contribute, one is the force at C, which is horizontal at this in this state, and the other is the weight, and we know the moment arms because the dimensions are specified. Therefore, I have this angular momentum equation. Note, in this angular momentum equation we still have some unknowns. Omega dot, the angular acceleration of the connecting link, that is not known. Therefore, what we do is we write down the linear momentum equation, Newton's second law, for the center of mass of the plate. Therefore, we need the acceleration of the center of mass Ag, and acceleration of center of mass is same as acceleration of point B. Once again, because this body is not rotating, the angular velocity is 0, angular acceleration is 0. Therefore, we have acceleration of g same as acceleration of B, and which is actually same as acceleration of C. If I now write down Newton's second law for the plate, for the center of mass of the plate, mass times acceleration of center of mass of the plate is equal to the net force acting on the plate. We have the weight and the two forces in the x direction. If I put in the expression of acceleration of g, which is same as acceleration of B, into this equation on the left hand side and look at the terms, the I cap equation, gives me minus m L omega square is the sum of the two forces, hinge forces. This is the I cap equation, and the j cap equation gives me L omega dot is equals to minus g. Now, I have omega dot from here, and omega is already known from our previous calculation. Therefore, I know the left hand side of the first equation as well, I cap equation. If I now substitute in equation 1, which is the angular momentum equation, I can solve for Fc. Fc turns out to be minus 1470 Newton. Now, this negative sign indicates that the way I have taken the force Fc in the positive x direction, that is incorrect, it is actually in the opposite direction. Therefore, Fc is, so according to this figure by Newton's third law, I should have Fc in this direction and F on the other end of the bar in the opposite direction, both are Fc, the two force member. But because now after calculation we find that the sign is negative, which means the bar will be under tension. This figure what I have drawn now shows that it seems that the bar is in compression, but if you reverse the direction of Fc, the bar is under tension. So, the actual thing is the bar will be under tension. What is the purpose of this equation? We can find out Fb as well from here. Once I have solved for Fc, I know omega and I can solve for Fb. So, that completes this problem. Let us move to the next problem, again from the book of Merriam and Craig. Each of the hinged bars has a mass per unit length rho and the assembly is suspended at O in the vertical plane. If the bars are released from rest with theta essentially 0, determine the angular velocity omega common to all bars when A and B and C and D come together. When this mechanism is fully stretched, you will find that A and B will come together and similarly C and D will also come together, and that will happen when theta is equal to pi, and it starts from theta equal to 0. I have drawn the 3 states, the starting state, the intermediate state and the final state of the mechanism as it moves. This is in a uniform gravitational field and there is no other active forces, therefore, the total mechanical energy of the system will be conserved. In state 1, which is the folded configuration initial, and state 2 is the final configuration, which is the stressed configuration, we have the total mechanical energy. Here in state 3, I have drawn some of the angular velocities of I have shown the direction of angular velocities of some of the links. These links will rotate like this in opposite direction. This is going to rotate like this. I have shown some of these omegas in the third state. Note that the potential energy datum has been taken in the initial coinciding with the ceiling at the hinge at the ceiling. The total mechanical energy at the initial state is 0 because there is no kinetic energy, and potential energy is also 0 because it coincides with the datum. In the second state, we have kinetic energy and some potential energy. Let us look at the kinetic energy expression first. As I mentioned, these two bars are moving inwards like this. They are hinged at O. I can write the kinetic energy of each bar as half I about O times omega square. At the final state, I can write down the kinetic energy as half I about O, the moment of inertia about O, times omega square, and I naught is 1 by 3 m times length square, 1/3 mb square, and there are two such bars. What I have done is I have written I O here, pulled out 1/2 here and omega square here. Now, let us look at the bar A D or B C. They are identical bars. The kinetic energy of these bars in the final state, they are actually moving or rotating about this point. This point has 0 velocity at this instant, because on the fully stretched condition, this hinge will come to rest, and therefore, this bar, these two bars are rotating about this fixed point. Therefore, I can write the kinetic energy of the bars A D or B C as half I about G times omega square. Omega remains the same for all bars, and I G is 1 by 12. The mass of this bar is 2 times the mass of the smaller bars, because the length is twice, and the length of this bar is 2b, and that is the moment of inertia of the longer bar A D or B C about its center of mass, and hence we have this as I G, 1/2 is pulled out, omega square is pulled out. Similarly, this point E at the bottommost point has also come to rest. Therefore, I can write for the two bottom bars, I can write the kinetic energy of half I E omega square, and I e is 1/3 m length square. Potential energy, this is completely stressed. The center of mass of the whole system is at this level, and from the datum it is at a distance of 2b in the negative, that is why minus 2b, and the total mass of the system is 8 m, and g is the acceleration due to gravity. Once everything is in place, I can make simplifications, and finally, I find that common angular velocity as under root 12 g by b, the length of the smaller bars. This completes this problem. To summarize, we have discussed the work energy relation and used them in some problems to understand their application, and we have looked at conservation of energy, solved problems based on conservation of energy. With that, I will close this lecture.